Hey, welcome back. How are you going with your congruence and similarity? Let's have a look now at a more formal mathematical proof of these two. And what we're going to do is then end up with an example of why we might want to prove two triangles are congruent or similar, and where that leads with geometry theorems in general. So let's have a look at these figures. Hey, looks like they might be a pair of congruent triangles. What do you think about those two? MNO and POQ. These two, whoa, I don't think so. They're the same shape, this top one and the larger one at the bottom, RQS and RPT. They could be equiangular and similar. One's the enlargement of the other. Don't know about these two over here. Oh, where does that fit in? Can you actually say that this triangle and this triangle are equiangular? Are they similar? That's the sort of thing we want to try and prove now, because there's a big value, as you've seen, in showing that two triangles are congruent or similar. We can find a missing side in one of them. Okay, let's go and have a look and see what we can do. So here are some guidelines, if you like, for proving that two triangles like these are congruent. So what are we going to do? We write the matching vertices in the same order once we have established one of these four conditions holding. Okay. So what we would do is list them all down, what's equal to each other, list it all down, and state the triangles in order, matching them up, and matching the vertices here. So CA, what's that equivalent to? GI, or another combination. So here we would say, listing all those down, that AC was equal to GI and AB was equal to GH, and that's all given, and BC was equal to HI. So then we could say triangle ABC there's an equivalent sign there. Some books have it with a squiggly line to mean they are congruent. And once we've said that, of course we can say, well, the angles would match up as well. They're identical. So angle ABC will equal angle GHI. So that angle in there would equal that angle in there. Quite powerful if you have some missing information in one of the triangles and you match it to the equivalent, another equivalent triangle, and find that bit of information. Let's have a look at an example from Pearson's here. So prove that these two triangles are congruent. Let's look at it. Name the triangles, MNO and PQO. I generally don't suggest people put that immediately. That's what you're trying to show. So I prefer that you put in triangles MNO and PQO, then do the proof. What have we got here? Well, angle MNO, that one, MNO, M, oops, hang on, I got that wrong. MNO, let's have a look. MNO, that one there, and triangle PQO are alternate because we're given these parallel lines. That little sign there meaning they're parallel. And in brackets you should put the reason. Angle MON, let's have a look at that. MON and POQ are equal, yes, vertically opposite. And we're also given, we've got two sides, MO equals PO. So what have we got? We've got two angles and a corresponding side. So now we can say that they are equivalent or congruent. And we could match up the remaining sides, because here if we write them in order, MN would equal PQ. So if you write them in order, you've got the match-ups. And then we could say, therefore, we can solve for PQ. So proving triangles are congruent enables us to find missing information if one of them has got a bit of information that the other hasn't. Right, come on down and let's do some in similarity now. Using tests to prove for similarity. Okay. Prove that these two triangles ABD and ABCD, the big one right around the outside, are similar. All right, so if you redraw the triangles, this is a good trick. Okay, so we're plucking this one out and swinging it around, and then looking at the other triangle, BCD, sorry, I think I read that wrongly before, BCD, so swinging that around and just comparing them. Now, can we see that they have proportional sides? Let's have a look here. BD to CD is the same as AD to BD. So they're in proportion there. Okay, so they're in the ratio, and they've got an included angle. So that means they could be nested, couldn't they? In there, so that was 8 and that was 12. Okay, 12 is to 18 and 8 is to 12. So that's the idea compared there. So let's have a look at that again. I just go back there, and I think I put the wrong thing down here. Let's have a look. BD to CD was the same ratio as AD to BD. And so that little triangle could have been nested in the other one, and you can see then the connection by that transformation of enlargement. One's been enlarged, moved out in the same ratio in both directions. Okay, so therefore we can put an explanation. The two triangles are similar using this symbol, and not everybody uses that, so you can just write the word similar, because two sides of one are in the same ratio and the included angles are equal. So it's like an SAS one for similar triangles. What you're trying to do is show that they can be nested and that there is a transformation called enlargement that will produce one from the other. And you would have equal angles as a result of that also. So you could say the angle up there is the same as this one, and this angle here is the same as this one. So you can get some extra information about the triangles from that. All right, so let's have a look at doing some proofs. Prove the following pairs of triangles are congruent and find the value of the given variable. So in other words, there's an x in each of them. So can you find that x? It may be an angle, or here's a p. It may be an angle or it may be a side. So you've got to match them up and deduce something. So that's the handy thing about being able to prove congruent or similar triangles. Okay, so have a good look at that. The solutions are right down the bottom. We'll take you there in a minute. And then question 2, prove they're similar. So looking for ratio match-ups and a common angle so that you can nest them and see that one is the enlargement of the other. All right, and we'll just go through each of these and I'll take you to solutions so you can toggle forward and look at them afterwards. So let's have a look at questions 3 and 4. Okay, and they're asking you just to work something out there as to what rules you need to establish congruence or similarity. Okay, think about those. I'll take you to the answers now. And so there's part of question 1 down to E. And you scroll down and have a look. Don't forget the setting out. Okay, and then let's do the bottom of question 1 into question 2. Okay, and then question 3 and 4, the answers down the bottom there. Okay, toggle back and forward and mark your work. Let's go on now and have a look at some slightly harder problems. So I'll just put this up there a bit so you can't see the answers straight away. You've got to prove that these are congruent in the first question there, 5, and that they're similar in the second question. Here's an interesting one. We have 3 triangles there. Now you have to think about that. Remember, redraw the triangles so that you get match-ups, I would say. Redraw the triangles so you can see what they look like. Okay, do you want to see the answers? Let's go down to the answers now. In 5 and 6, you may need to put complete working there. And I don't like starting like this. You're starting with the statement. Oh no, the angle, that's all right, sorry. I thought they were putting the triangles are equal there. That's all right. Starting with the actual, come down. Starting with the actual angles that were given as right angles. That's all right. And then ending up with the conclusion that they're congruent with the reason. So there is a protocol, a accepted convention, a solution if you like, to really make a good proof here. Okay, well mark your work. Let's go on and try some other interesting ones now. Here's some reasoning and open-ended ones from Pearson's again. Explain why not a pair of shapes is similar if they are any 2 rectangles. So this is trying to argue it out, why not a pair of shapes is similar. Would any 2 rectangles be similar? Would any 2 squares be similar? Think of them having, must be what? Equiangular and sides in proportion, leading to being able to connect them through the process of enlargement. Okay. All right. And then the open-ended questions here, and just drawing your own triangles to show you know how to make them congruent or identical. Let's have a look at the answers to those. There's 7. Just an explanation of those. And then let's have a look at 8. And comparing them there, an example of each of the 4 rules. Okay, so we sort of did that at the beginning of the last presentation, didn't we? Introducing congruence. All right. See how you're going now. Let's go on and have a look at a question. Here's my question. What is the use of showing triangles are congruent or similar? Well, we've seen a big use, and that is, if you have a matching triangle, if you're able to show that 2 triangles are congruent, let's do another one over here, written the other way, and we match up sides, and so let's say, what's that one? That one. Those 2 are equal, and these 3 are equal down here. Then, if I know that this angle here is, let's say, 30, then I can say the equivalent angle in the other one is 30. What is it? It's the angle between that side with 3 strokes on it and this side. So, given some information from one, we can find out information in another. Could be very handy in researching or solving triangles and finding out sizes of angles. But there's another thing, and come down here, and that is, in geometry, we often have theorems. We just put this up the top. Here's a theorem. The line joining the midpoint of 2 sides of a triangle is parallel to the 3rd side and half its length. Many of these theorems were attributed to Euclid, and we use them to prove aspects of shapes in geometry. Are lines going to be parallel? what line is going to be equal to another. And so we can use congruent triangles and similar triangles to prove this one. Let's have a look at trying to prove it. Well, here's an interesting figure here. What we're trying to show is that MN, so M to N, is parallel to BC and half its length. This is a powerful one, isn't it? Well, just from knowing that M is the midpoint of this side and N is the midpoint of that side. This theorem says that if you join two midpoints, you create a line MN, and we'll put this, MN will be parallel, is what we've got to prove, to BC, and MN's length will be a half of BC's. So that's a pretty powerful result. Let's see if we can prove it. So let's go back to this figure, and what we're going to do is we're going to extend the line MN out here, and we'll draw a line CD here, which is parallel to BM. Now the interesting thing here is that we can show that triangles, what is it, AMN is the same as D. Where are we here now? So, we extended CD out, and MN intersected at D. So the triangle AMN is equivalent or congruent with, let's match it up, AM is going to be CD and AN is NC. So here it's going to be, AM is going to be the same as which angle here? C, and CN is going to be the same as AN in length. So this is going to be CND. Okay, and that would be the matching sides of our triangles, and we'd have to prove those congruent. So let's have a look. How could we do that? We have this side and this side equal. Now, with our parallel lines, what can we do? We can say these alternate angles are equal and these angles are equal. So we actually could have two angles and a corresponding side here. Okay, and from that, of course, we can say that CD here is also equal to AM. CD would be AM. Okay, C and D would be AM. Is that right? Have I got that right? CD and AM. I should have put that in a different order, I think. AM, yes, I have it in the wrong order. AM should be equal to CDN, because what we said was AN, that one to that one, should be equal to C to N. That was given as equal. So I had that in the wrong order. And so here now we can say CD equals AM. So that equals this one up here, also equals that. So now we have a parallelogram. So if we put that, AM equals CD, therefore BM equals CD, therefore we've got a parallelogram. MBMDC is a parallelogram because we've got one pair of sides pair of opposite sides parallel and equal, and that's enough to establish a parallelogram because we've got two parallel sides and they're equal. So what does that mean? Well, MN will be parallel to BC, so that's half of our result that we needed to prove. And also, if we look back at our congruent triangle, MN is equal to DN. MN equals DN, Therefore, MN is a half of BC, because opposite sides of a parallelogram are equal. So this side equals this one, and MN is half of it. So we have done it. We have shown the midpoint theorem can be proven that way. All right, is there another way of proving the midpoint theorem here? So let's go back and tidy up the diagram again and say, what else could we do? Could we use similar triangles? Okay, so similar triangles, what would that involve? Well, we can say we're working in triangles AMN and ABC. We've got angle A is common in both, and the sides around it are the same, right? Here, in the same proportion, sorry. AM and MB are the same, so AM has been enlarged to AB by a scale factor of 2. It's twice as far because these two are equal. And AN has been stretched or enlarged by the same amount, a factor of 2 times. So what have we done? We've got AB to AM is the same as AC to AN. Well, that's enough to show that they have been enlarged. Triangles AMN, ABC have been enlarged and are therefore equiangular and similar. So we can say they are similar under that notion. They've been nested, and you can see the ratio is given as the same. They're coming from that common point with a constant angle, and therefore what can we say? MN to BC will be in the same ratio. It'll be 1 is to 2. Should put BC over MN. Okay, so let's just get rid of this one down here and try and do this completely. So if we do it in the same order, we're doing the larger triangle, so BC over MN equals 2 is to 1. That means MN is a half of BC. So there's our first result. Now what about the parallelism? What about over here saying, are they parallel? Well, if these two triangles are similar, we said, by proportion and that common angle, what can we say? Well, angle AMN will match angle ABC, and ANM will match ACB. Okay, so we've got angle AMN equals angle ABC, similar triangles. Alright, and these are in alternate positions, so therefore they must be parallel lines. MN must be parallel to BC. So that's another way of coming at that idea of if you join the midpoints of two sides of a triangle, you create a line here which is parallel to that one, and it's half its length. So this is the interesting thing in the general development of theorems in deductive geometry. Congruent triangles and similar triangles are often an important tool in establishing theorems. Example here being the midpoint theorem. So as you go on more with geometry, these are going to be important tools. So I hope you're enjoying this sort of puzzle solving here, because it's very useful stuff in geometry. All right, look, well done for sticking with this, and I hope you've built up some skills, and I might catch you in another presentation. Cheers for now.